All right, guys. So we're winding down in this applications of derivatives portion of the course. Um, these I would say can be up there in terms of difficulty. It's going to rely on, if you guys recall, your implicit differentiation. Okay, so you differentiation. So you guys are going to need to know. Sorry, I can't talk and spell at the same time. You guys are going to need to know this. Okay, this is going to be critical to your success with these questions. Okay, so the first thing I'd say, I don't know, this is just a sort of steps for solving. And if this question's simple enough that you can kind of picture it, sometimes we don't necessarily need the sketch or the label. But typically we could say, okay, 6 steps here. You'll make a sketch and a label, introduce a variable, identify any quantities that you may or may not know, okay, and then find an equation slash formula that relates the variable that you've introduced to what it is you're looking for, okay, and then implicitly differentiate and solve right for a conclusion, okay. So what we'll do here is I'll make a short video on, like, we'll do a couple questions on circles and squares. Today is all these kinds of questions, okay, and I'm just going to run you through as many of them as I possibly can so that you've seen them all, okay, and then there's some homework questions associated with this stuff, okay. So we have circles and squares, and then we have some cones and cylinders. I don't know why I've got the same. Oh no, we're okay. And this afternoon we'll do some like troughs and cones and hemispheres and things like that. Okay, so just different shapes. And really what it comes down to is we're gonna write down an equation and then implicitly differentiate it and solve for the thing that we're looking for. Okay, so here, how fast is the radius changing when? Okay, so we're looking at this oil slick that's spilt or something like that, right? And it's increasing at 150 meters, or at a rate of 150 meters per second squared. Okay, so it's how fast is the radius changing when we are, that big versus when the area is 100 meters or 1,000 meters squared. Sorry. Okay, so I would say if we're talking about area and circles, chances are we're going to be talking about area equals pi r squared. Okay, if we were interested in differentiating, okay, so this is your implicit differentiation skills coming into play here, right? Ultimately, we're interested in finding, how is this changing relative to time, right? So ultimately, what I want to do is say, okay, well, I want to find dA by dt, right? This is I want to differentiate this equation because differentiation tells us the rate of change, okay? And so if I were to differentiate this equation with respect to time, this is the important part, right? Because that's how it's changing. I'm going to see that I get pi r, sorry, one sec. We got to differentiate this side as well. Sorry. Okay, so we need to differentiate this side with respect to time, okay? But there is no time variable, right? And that's at the heart of this implicit differentiation concept, right? We can differentiate this, no problem, okay? But we need to define or state how we've differentiated it, right? So we can find the derivative of this by saying, okay, well, pi is a constant, so if I was to do product rule, I would like the first portion of this would be 0 because, you take the derivative of a constant, it disappears, right? So we really have a situation like this where it's 2 pi r. Now, you've differentiated, no problem, right? We've just applied power law. But the problem is, and you guys will remember, when you differentiate something with respect to a different variable, you have to treat it like chain rule. And so we have to multiply by dr by dt. Okay. Now, if we stop at this point and we take a look at what's been given to us in the question, it told us how the area of the oil slick is changing. It's increasing at a rate. Well, this here, the area of the circular oil slick is increasing at this rate. That sounds like area rate. Well, that sounds like dA by dt. Okay. And we also know the radius is 25 meters. Well, we know what the radius is. And what is the thing that we're looking for, I suppose, is the point of this question. How fast is the radius changing when? Changing radius with respect to time. Okay, so now we can just plug in all the information that we have, or we could do some isolation, right? We could say, okay, well, I know dA by dt might be a little confusing if we don't plug in a number. So why don't we just plug in the numbers first? Okay, we get 150 is going to be equal to 2 pi times 25, and that's going to be multiplied by dr by dt. Okay, and now I could divide both sides by 2 pi, or 50 pi, I suppose, right? 2 times 25 is going to be 50 pi. So I could say 150 divided by 2 pi times 25 will equal the rate of change of the radius. So I could type that into my calculator and find out that we're going to see dr by dt is going to equal 3 over pi meters per second. Okay, guys, these are interesting questions, right? They're kind of powerful from the standpoint that we could find out. I think the most interesting part of this is that the rate at which something is changing is always changing, right? And that's what we define acceleration to be, right? And so we could find exactly what the rate of change is, like how quickly something is growing at any particular radius for this kind of question, right? So what happens though if I'm given the area? Okay, and I suppose we're like, okay, well, you know, we're just switching the information that's being provided to us. This question hasn't really changed, right? But we're switching the information that they're providing us in the question, right? We could say, okay, well, we still know that the area equals pi r squared, right? That hasn't changed since grade 4. Okay, now the catch here is though they've provided me with the area in this question. So if I were to find the radius here, then I could repeat this question, okay, above. So turns out when you go to isolate for everything, we're going to see that r is going to equal the square root of 1000 divided by pi, which actually works out to be 17.84 approximately. Okay, so we can use this to redo this question, and we can compare the two rates, right? What's going to be interesting is how quickly is it moving at a larger radius versus a smaller radius. That's kind of an interesting question. Is it faster? Is it slower? Right? So let's find out. We can still use the exact same equation. We're just going to replace the r value in our equation from above, right? So we're going to see dA by dt, right? It's still going to be the exact same equation, right? 2 pi r multiplied by dr by dt, and we're just going to re-isolate for dr dt. Okay, or I suppose you could just jump down to this line for simplicity's sake, right? We could say, okay, well, dr by dt is going to equal 150 divided by 2 pi times 17.84. Okay, and if you were to run through that again, you would see that dr by dt, okay, is going to equal 1.34 meters per second. Okay, so down here I actually gave a numerical answer. Why don't we go up here and actually find a numerical answer? I didn't have that in my solution here, so let's say 3 divided by pi. Let's just say 3 divided by pi, 0.95. 955, I suppose, meters per second. Okay, so this logically supports some of my, like, at least maybe you guys had a different hypothesis as to what's going to happen, but my hypothesis is something. If you guys ever looked at like, if you've got, like, let's say instance, if you spilt coffee on a countertop or something like that, right? My hypothesis based on that experience would be that if the radius are smaller, so like time-wise relative to when you've actually spilt the coffee. When the radius is smaller, it's moving quicker. Relative to, once it's spread out onto the countertop, it's moving at a much slower rate, or it's growing at a much smaller rate, right? So this process supports that hypothesis. Okay, interesting question, right? And all we're going to do today is take our familiar equations. This is what's kind of fun about this. We've been using these equations for a long, long time. And now we get to take them and apply some new math that we've learned this year in calculus, right, to solve and contextualize different things around things that you would see in your everyday life, right? Where you were starting, we can put math to something, right, which is kind of cool. It's always fun to be able to do that. Okay, so what about in the event, like how fast is the area of a square increasing when the sides are 6 meters in length and growing at a rate of 2 meters per minute? Okay, this one I'm having a harder time giving you a real life example of this, but nonetheless, there's a square and it's increasing at a rate of 2 meters per minute. Okay, so I would say square. I would say you're still going to start at the fact that area is going to equal length times width. The nice thing about a square is area is actually equal to either the length squared or the width squared. We'll call it S for side length. Okay, S for side length, we're going to say, okay, S squared. Okay, and so we could differentiate this as well. Okay, we could say, okay, well, what am I looking for? Well, let's find out in a second. Okay, well, let's actually differentiate this implicitly, and then we'll put our information back into here. Okay, so we could say dA, how is the area changing with respect to time? Well, that's going to be the derivative of the right side. Well, the derivative of the right side with respect to time has to be an implicit derivative, right? So we're going to have to say, well, 2s multiplied by, well, how is the ds, like how is the side lengths changing with respect to time? Okay, and we know all of this information in here, right? It told us, how what we're looking for is how fast is the area increasing, because we're looking for dA dt here in this particular question. But we know at one moment in time when the side lengths are 6, that's going to be our S value. And then we're going to know that the length is growing at a rate of 2 meters per minute. Okay, well, that's this. Okay, so we'll just plug that information in. dA by dt is going to equal 2 times 6 times 2. And dA by dt is going to equal 12 times 2 is going to be 24 meters per minute. Okay, and it should be meters squared, sorry. Sometimes if you guys include the units, you would see through dimensional analysis, you would see that the units come out. Sorry, that's my bad. Anytime you talk about area, obviously the units have to be talking about the meter squared, right? So there's a little introduction to you. I would say, like, obviously with more simple equations, the implicit differentiation is easier. Okay, but if you want to find anything that's how anything is changing with respect to time, we can differentiate implicitly and use the information provided us in the question to answer alternately or find what it is we're looking for. Okay, it's just, I think the new information here is interpreting what these mean. Okay, and extrapolating information from the question and plugging it in the appropriate positions. Okay, so I'll hit stop there. That'll be part 1 for this video. These are kind of fun questions for today. Okay, they're hard, but they're sometimes fun. Okay, depending on the context of the question and what it means to you. Okay, so anyway, I'll hit stop there and I'll see you in part 2.